Can you see the presentation?
Yes, we can see.
Okay, cool. So what was it? Wednesday, and we finish here, and basically this was the basics of a technique that you might need to use at a certain point, and it's kind of depending on the type of selection that you use, whether you use intensity to select data, or as we saw, colors. We go in the harness intensity diagram to select data in different regions of this diagram. There is nowadays a technique that is being used also a lot when you have a periodicity or quasi-periodic oscillations in the data. And basically, there are different ways of calling on this. This is intensity resolved spectroscopy, time resolved spectroscopy, phase resolved spectroscopy, and the names basically are linked to the way you make the selection. So in this one, I would have said something along the lines of color code diagram selection or a spectroscopy if you were going to divide the data in this way. But Sunil was asking me about the spectral timing in terms of phase resolved spectroscopy, and this is exactly what we're going to talk about now. It's always better to talk with examples where you can actually see the things by naked eye. So on the right part of the slide, you see two light curves. On the top is a source called IGR J7091, and on the bottom is GRS 1915. And what I want, so what you have is, as usual, that the x-axis is the time, and the y-axis is the counts per second. And one thing that you will notice is that this source reaches, so 1915, the bottom one, reaches about 5,000 counts per second when it shows these oscillations. While the other one, which shows oscillations that are very similar in shape, only reaches 200 counts per second. So it's an order of basically 20 more, 1915 respect to IGR. So for now, for a second, let's focus only on the lower one. What you can do when you have a lot of statistics, or when you have a lot of counts, is actually, as I was saying, creating color for each of these points. And if you create a color for each of these points, and again, just as a reminder, it's defined somehow as the ratio between some ones of your choice, then you can create the plot on the left, which is basically shows a kind of loop, where this part here, it's basically this part, and then the loop that is being done by each of these flares. So by doing this color code diagram, on, in this case, harness intensity diagram, with data that is of good quality, you can already see that there is an evolution of the energy spectra, and that energy spectra, or that evolution, is always in the same direction. It goes like this in time, and it comes back like this in time, where this part, you can identify it as the decay, the fast decay on the flares. So this is an ideal case. What you would like, and it's very clear when you do colors, ideally you would like to do energy spectra for each of these points and see how it evolves. But that is actually more complicated, because now I did have enough statistics for creating colors and of course the intensity, but the energy spectra, you are spreading suddenly all the photons into many energy bins, so your statistics go down. Before I continue, can you actually see me, because I'm starting to play again with my hands? I cannot hear you, so I don't know whether you are actually even hearing me.
Yeah, we can hear you. Yeah, we can see you now.
Okay, thank you. Okay, so now I go to the example on the top, where again you see the flare, and you would like to check whether, in terms of hardness intensity diagram, you also see this loop. And you see it here. The error bars are much larger, but there is a catch. This is not possible to do for each flare. What I had to do is certain type of average among many flares to be able to create this plot on the left. So again, while in the bottom, I was able to do it for each flare, here I had to do some kind of average. So how do you do that average? So what you do is it's a technique that is called folding, and it has actually many names, but that's the one that I use. So you take the light curve, you calculate a period, you cut your light curve in that period, and as you can see there, it's not perfect, but it is what it is. And then what I do is I bring this one to here, I average, and then this one to here, I average, and I bring this one and here an average, and so on, until I have actually one average profile made out of all the flares that I have, where I define where it starts and where it finishes based on that period. And what I end up having, it's an average profile of that flare. Now, if you have that, then now I can calculate the color for each of these points. And that is what you see here. This loop is created by doing first folded light curve, creating GTIs, as you remember from Wednesday, of each region, and then calculating the average color, the average intensity in each part of this profile. What are the pros and what are the cons of doing this? Well, the obvious pro is that you are able to reduce your error bars, and you are able to test, as in this example, that you are actually seeing a loop as well. But it has the negative part that you might be averaging things that it's a mix of stuff. So if I come back to here, you will see that the beginning here, it's actually like a little flare here. Probably it's okay here. Here I missed the beginning. The beginning should have been somewhere here. The same here, probably here is okay, and so on. The underlying assumption that you are making is that if you average enough of this data and enough of these periods, then the final profile will be representative of each of these single flares. So one thing that you must do if you ever use this technique is actually to do the profile and check that the shape that you find is representative or similar, at least by eye, to what you were seeing in the data. If you were to put the wrong period, or this is not periodic enough, you might get a profile that it looks like this. And then if the profile looks like that and it has 3 peaks, clearly you see that cannot be done, and that's not correct. So you have to do other things. There are other techniques, and if any of you are interested in doing this, I can suggest you a few papers. But what you can do is, for example, saying, okay, I'm going to write an algorithm that finds all the lowest points in each period or close to the period, and then you fold on that. But of course, that has the other problem is that you have different number of points in each interval, and then you have to solve for that. So, and just as things to remember, every choice that you make will have its pros and cons. And it's important that when you analyze your data later on, you remember about the assumptions that you made, and of course, you are careful when you make your interpretation of the data. But so far, we were doing this by eye. In many cases, we just can do that selections by eye or using spectral colors, because literally you don't see you don't see the oscillations as clear as there. So basically, the bottom line is statistics kill us, but we have some guy, Sir Fourier, that comes to our help. So this is actually the light curve that I wanted to show you. And again, now it went wrong in something. But basically, this light curve shows a power spectra with this peak, without this peak. But this light curve here shows a power spectra, or a power spectra that shows this very nice peak at 2.5 hertz, or about 3 hertz. So we have, give me a second, Okay, so this means that we know now, given a particular technique that we will discuss briefly in a minute, that even if we don't see anything by eye here, we do have a periodicity, which basically is about 3 to 5% of the variability that you see in this light curve. And we know that the average frequency. We don't know actually the real shape of that oscillation, whether it's a sinusoid, and actually we know it's not a sinusoid, but we can actually use that to try to do a very similar idea to this. But now we don't select it by eye, we select it by period. Okay, so this brings me to the composition of functions as sine waves, and this is what we're going to see now in a second. So if you have a wave that it looks like that, hopefully most of you at certain point at uni, you have seen that you can actually create this wave by having two different sinusoids. One that it goes really fast, and this is where you see this, and another one that actually is modulating that first sinusoid, that is basically another sinusoid. And the wave A, that is the one plotted here, is basically one sine times the other one. What always surprised me, and the very first time that I saw this, is the fact that if you had something like this, a square-shaped sine wave, you can actually prove that you can represent this as a sum of sine waves. And for me, has always been kind of like, at least at the beginning when I saw it at uni, it was either magic or it was a lie, because I couldn't think that something that has these shapes, very smooth shapes, could create something that is square. But actually, this all comes from the work done by the Fourier, and there is a lot about that, and we will be uploading, for those ones that do timing projects and are interested in it, we're going to upload 2 lectures recorded here in Southampton by Tommaso Renoni, who's going to be there later today, where he goes more in depth about the Fourier transform. So right now, I will just say Fourier transform is this, where basically tells you that any function that you have can be written as a sum of complex exponents, or basically sines and cosines. And what is important is that you have this AK that are the Fourier coefficients or amplitudes of the different waves that you add different signs that you add to create your signal. My guess is that so far you are completely lost on what I'm saying. So let me actually show you a very old video that I found that explains exactly what I was saying. And there are better versions in YouTube, but I left this one because I thought, okay, this one is probably the oldest one that I found.
A periodic waveform is one that has a shape, which is repeated at regular intervals of time or periods. To illustrate how the Fourier series may be used to represent complex waveforms, let's first apply a single sine wave to a square wave with period t. To construct a sine wave with the same period, we draw a vector and rotate it one revolution per period. The vertical projection of the vector tip oscillates up and down once for each revolution of the vector. When the projection moves to the right at a uniform rate, it draws a sine wave. To estimate how well the sine wave represents the square wave, we can superimpose one on the other. The approximation is only fair. The error is about 19%. Next, we tried the same fundamental, or first harmonic, and the third harmonic. If we stop the action momentarily and add the vectors, the sum produces a waveform. Which obviously is a better representation of the square wave than was the first harmonic alone. How much better is shown by the superposition test. The error is about 1/2 as large as before. When 3 harmonics, the first, the third, and the fifth, are added, the resultant waveform is an even better representation. If we again superimpose, we find the error now down to about 7%.
So you get the idea that how you can actually represent a square function with a sum of sinusoids. So here it's what is happening. So you have the red function, you use all these sine waves, and each sine wave will have a different, well, of course, frequency, and each different amplitude. And what you see on the top is the original function, and what you see on the bottom, again, we will play it again, is the representation of the same function, but in the frequency domain. What it means is that now what you are having is that here is in time domain, here is frequency. Each of these has a different frequencies, and the size, let's say for now, of this tells you about the amplitude of that oscillation. So by doing this plus this plus this plus this plus this plus this, you can actually produce this thing here. This is a big thing because this allows you to do a lot of stuff. So coming back to the formula a bit, basically, if you take the Fourier coefficients and you actually do square of that, this is related to the amplitude of well, I have to play it again, of those blue lines or the amplitude of these signals that I was talking about. So let me show you some of the applications for this. And we will talk briefly about something that's called the dynamical power spectra. So what happens if you have a signal, and now it's a sound signal, and you do a Fourier transform again and again and again in units of, for example, 1 second. So this is a 3D representation of that, where you have frequency, you have time, this is time, this is frequency, and in the z-axis is going to be the strength of the signal or the amplitude of the signal. So you see all these kind of mountains that basically tells you how strong the amplitude of a sinusoid is at that time in time. So let me actually give you a real example. Most of you probably don't even know where these sounds come from, or maybe your parents have been able to show you, but this is, okay, let's go for it. That was the old way that we would connect to internet. And you would call a number, it will connect, and it will do all those noises. And let me go through this again, but let me explain. So again, now it's time. I don't know if I can draw the here now. In this side is time. This is frequency. So the frequency of the different sounds that you are hearing, hopefully hearing. And in colors is the what is it? The amplitude. And if I come back to that in a second, let's see if this works. We go again. That's the telephone we're calling. And this is when it starts communicating and setting the link. So you can see on the top the link to YouTube, so you can look at it later yourself. So let me just go briefly with something that is related to all this, and just to show you how some people in the recent years, in the last 20 years, have become multi-billionaires just by using a technique that has been invented a long time ago. And nowadays, there are more of these type of applications, but there is one that is called Shazam, that is basically on your phone, and you hear a song, you record a bit, it's just a tiny bit of that song, and it recognizes which song it is, and it tells you. So it works by actually doing basically a similar thing to what I was showing you just now. So it creates a dynamical power spectrum. So in this axis, you have time. In this axis, you have frequency. And in black is basically the amplitude of the different sinusoids that represent your music. And what they do is, for each song, they create a fingerprint of the whole song. So and all those fingerprints are pretty different, or different enough so you can differentiate one song from the other one. So what these people did is to say, okay, let's record a bit of a song, 5 seconds. They do a dynamical power spectra, so they create a fingerprint like this one. They find, let's say, best points to study, and then they compare this fingerprint with their data set, database, the full database. So by comparing this with their full database, they are generally able to recognize which song it is, and then they tell you. And this process nowadays takes a few seconds. But this is a big thing using a technique that has been used by people for many, many years. So this is the kind of things that you say, well, is this technique only used in astronomy? No, it's used everywhere. You have it on your phones and telecommunications. Actually, we're able to talk right now thanks to these techniques or similar techniques. But anyway, coming back, so of course I have been a bit on the loop, and in the sense that I've been talking about power spectra, quasi-periodic oscillations. I'm pretty sure that some people have been talking about red noise. But what does that look like? Okay, so first on the right, I'm showing the power spectra. It's frequency and power, and again, power is a measurement of the amplitude of a given signal. And you can have coherent pulsations. Coherent pulsation is basically you have a perfect sinusoid. And then what you get in the power spectra is almost like a delta Dirac, just a step function, and not like the one I draw. If you have a quasi-periodic oscillation, so an oscillation that is pretty much coherent, but it's not perfectly coherent, so it's not a sinusoid, then you get what is called the QPO, the quasi-periodic oscillation. Now, before I move on, you can have a quick QPO because you change the frequency, but the rest stays the same. Or you change the amplitude and the rest stays the same. Or even if you change the phase and the rest stays the same. And as you can imagine, if you shuffle all of the other ones as well a bit, then it will also create a QPO. And you have what is called the red noise, that is variability that you see in the light source that generally will produce a power law like in your power spectra, sorry. So this is the real, comes from real data. This is in this on the top left, this is a pulsar. So that's what you get. It's a power spectra that has nothing except this thing here, and basically tells you the exact frequency or spin frequency of a neutron star. This is how a QPO looks like. This is peak noise, so it's something that is in between. Sorry, let's put this is broadband noise or red noise, and there is something that is more called peak noise, that is a mix between a QPO and a broadband noise. And I will not go into details to that because basically there is a lot for you to understand about how this power spectra evolve and what we mean with this. But the important thing is that you know that there is this kind of a broad feature in the power spectra that is variability similar to this. And then that you have the QPOs, and if you have a pulsar, then you have this coherent oscillation. So, as I was saying, this some reason is repeating it. It's not correct. That should not be a QPO there. It doesn't matter. You cannot see it by eye. But what you need to take from here is that timing analysis really sometimes, at least for me, still. It seems a bit like magic, because it can reveal features in your data that you would never be able to see by eye. And let me give you an example. I didn't put the plots, but I know I actually show it, I think, later. We found a pulsar of a neutron at 400 hertz, I think it was. So let's put it like this. We have observations of a neutron star. We only get 30 photons a second from that neutron star, which is rotating about 400 times per second. And the amplitude of that oscillation is of a few percent. So let's say 10%. 10% means that 10% of your photons come from the neutron star rotating of the pulsar. So if you have 30 counts per second, 10% is 3. So I have 3 photons from the pulsar itself per second. But the pulsar is rotating 400 times a second. So that means that it rotated 1,200 times in 1 second, and only of those 1,200 times, I got 3 photons. Well, the Fourier transform is able to detect that signal if you integrate long enough. So now let me go actually stop for a second and talk about something that is called the number of trials, because this is something that many people forget, and even today we find papers where they haven't taken into account the number of trials. The number of trials is basically the number of experiments that you do when you are looking for something. So if you find a signal that you think that is real, and you calculate the probability that that signal is real, when you calculate that probability, you need to take into account how many experiments you did. As an example, if you threw the dice and you have a 6, you can say that if 6 is the maximum, you say, oh, I am very lucky because I got a 6. That is correct if you throw the dice only once, but if you threw 100 times and you only got 1 6, you are not so lucky. You are actually very unlucky. So the number of trials is that number of experiments that you have done until you found the event that you are interested in. I will not go in more details about this, but please remember, whenever you find a signal in your energy spectra, in your power spectra, you need to take into account the number of trials. Otherwise, you are not doing it right. Okay, so coming back very briefly to this dynamical power spectrum that I was showing you before, this is another example. This is a neutron star, time again, frequency, and this is what it's called kilohertz, peak at 800 hertz in average. And with the dynamical power spectrum, you can see how the frequency is moving. And what is cool about this is that if you can associate this frequency to a physical process, like for example, if this frequency gives you the inner radius of the disk, then suddenly you're measuring the inner radius of the disk of an object that you cannot see because it's really, really far away. So it's pretty cool what you can do with this. And actually, I talked too fast because actually now comes the example that I was telling you about the pulsar. If you have a low mass X-ray binary, companion star, accretion disk, and here in the middle you have a neutron star that looks like this with its magnetic fields, can create a pulsar at about 400 hertz in this case, and this is the power spectra again. And if you do actually the dynamical power spectra of this pulsar as a function of time, you also see that the frequency is changing. So the frequency is not stable. And this plot, you would have said, oh, okay, this is the frequency. It's just one number. That's it. But when you actually do a dynamical power spectra, you see that it's changing between 435.305 to 0.330, which is a significant change in frequency, even if it's tiny. This change in frequency is what is produced by Doppler effect that it's given by the fact that the neutron star is in a binary system, and both the companion star and the neutron star are rotating around the center of mass, wherever the center of mass is, probably somewhere here. So this is what we use in many, many projects to try to find out the orbital period of the system out of thanks to the variations in the spin period of the pulsar. Because it's worth mentioning, if you don't know about it, that a neutron star rotates very fast, but the spin or the rotation doesn't change very fast, and you need years to be able to see a variation on that. Now, I'm coming back to things that we've seen before, just to close a bit what we've been seeing. This is the pulse profile of one of these pulsars. So now it's about the pulsation itself. And what you see is the pulse profile at different energy ranges. So these are the different energy ranges. And you see that they are similar, but not exactly the same, which gives you something about the physics or the physical processes that produces this lighthouse effect. And what you can do again is actually cut it in pieces, fold it, and then do energy spectra, create energy spectra of each of these phases, and then out of it, try to extract spectra that will allow you to understand how the spectra varies. It's worth mentioning that power spectra is a technique that is very, very sensitive to mistakes. So to find things that are also not real if you are not very careful. So what I'm showing you here is of an observation with HST. And you have the frequency again, and this is the power. And you see some kind of weird shape here. But what is more important for me right now is that you have a lot of peaks there that at the beginning we thought it's this super nice result. It could be that it was a source that had several kind of peaks related to something we didn't know. But when you zoom in, you see that there are too many, and it's very difficult to see single astrophysical objects showing this type of peaks. And then we dig into it, and basically we found that it was a rounding problem of the numbers of the times of arrivals in the HST data. When you solve this numerical problem, then the peaks are gone. So I show you this example because if you find anything that looks too cool or too complex, and it hasn't been published before, then you have to start wondering before you actually can it be that is something going wrong here? Many times you will find that, unfortunately, because that's the bad news, it's something that is wrong with the data analysis. So I'm reaching already the end of my talk. I just want to talk very quickly about a few things, and then this is all more explained in the lectures that we're going to upload later today. But basically, when you do a power spectra, you have a time sample. So basically, what is your time resolution? And your time resolution is going to define which is the maximum frequency that you can actually study in the power spectra, and that is called the Nyquist frequency. You also have the lowest frequency that you are going to be able to sample in the power spectra, and that's related to the time span T that you are actually able to study, or that you take in your data set. And these two numbers, are very, very important. I just wanted to bring them here because independently of what software you use, you will always be asked about the time resolution and the time span. And they might call it in different ways, but those two numbers are key when you create a power spectrum. But just coming back to one more thing in terms of techniques and what you can get off some of these systems. And it's something that is called time lags. And nowadays, a lot of people are working on this. So for example, imagine that you have your disk, you are somewhere, you're an observer somewhere here far away, and you have photons that will reach you directly, but there are photons that go from this that we call corona, are emitted in the direction of the disk, they hit the disk, they are reflected, and then they reach you. So come from the same process, and there is a connection between them. So for example, there is an oscillation there, then you know that this one will arrive before this one, just because there is this extra length of space that the photons have to travel. And because the photons travels at the speed of light, you actually can map the disk in certain way. Now, this is very complex. In this image, it sounds very simple, but it's very complex when you bring it to reality. This thing that it's the way we study systems very, very far away. It's also what is used when you go, for example, to a concert. So you are sitting somewhere here. Red on red is not great, but I hope you see it. And the music is coming directly to you like this. But you also have speakers here, or you might have speakers here. And the music basically has to go to the speakers, and the speakers then emit sound that goes into your direction. And when people set these amazing concerts, they have to take into account the fact that most people should be able to hear the one time the song, and not that they are hearing echoes, because the music coming directly to here arrives before the one that is coming from this, and then you have music that comes later to here. So I hope, I don't know if I explained it well. It's much easier when I'm there with hands, so I apologize for that. But basically, this time lapse of phase lags as well, you need to take them into account in a lot of areas of sound research or sound experiments here in Earth. What is it? But we also use the same techniques to study black holes or accreting objects. So basically, the bottom line is that if there was a change in of one signal respect to the other one, the second one had to travel a bit longer, what you will see is a change of phase. So as you will remember, hopefully you can write sinusoid as a sin I 2 pi f t plus phi, where phi is that phase, and is the phase is that the one that specifies when the cycle starts at t0. So if you have, for example, the red one is your original sinusoid, and you have another one that is now here represented in blue. This is what we call the phase shift. So how much it has changed in phase. And that is related to, for example, how long it had to travel one respect to the other one. This is, for example, an different example. So this is a phase shift of 90 degrees, where A is ahead of B. And this is the same, but now B is ahead of A. So this is an important thing to take into account. This example shows you a phase shift of 180 degrees. So basically, they are mirror images of each other, if you think about it. And the important thing where there is no change is where A and B are on top of each other, and you say there is a phase shift of 0. So coming back to this, how do you study this? Which is the techniques that you study to do this? Basically, the magic word is cross-correlation. The cross-correlation, where you do basically a convolution between two functions, and I'll come back to that. It's mathematically defined by this. And what you are doing is taking your first light curve, you take two light curves, 1 and 2, that look similar, and then you put them together, and then you convolve them. Now, how does that look in an example? Is this. So you keep blue steady, and then you move red and you multiply one by the other one, and actually you do the integration. And what you get is this lower part, where basically it's telling you where the overlap maximizes. And as you see, I cannot draw, but it shows a peak at about 2 seconds. And 2 seconds is exactly when the two things overlap. Given a problem with time, I won't be able to talk about all this, but I just want you to know about it. You have the convolution, you have the cross correlation, you have the autocorrelation, and they give you slightly different information, and you use them for different purposes. If you are going to get into this, then we should sit down and talk about it. Tommaso as well knows a lot, Mariano. So many of us can give you a hand. It's not a difficult technique to use. It's a technique that is rather difficult to interpret the results. But yeah, it's something that you might want to go into, and it actually gives you a lot of really cool information. Of course, sorry, I forgot Dan is there as well, who is an expert, and he will be able to tell you a lot about it. Just a quick thing, in terms of coding this, Python already has a lot of stuff there, but I always recommend the numerical recipes. These are books where basically goes straight to the point. They tell you, this is this is the autocorrelation, you use it for this, and this is the code. You're not interested in the code right now, but the explanations of the techniques of what they mean and what they do are really great in here. And if you go back to the old numerical recipes in Fortran, for example, they are for free. So you can actually download them there. And you don't need to download the one in Python to understand the technique. You can just do the Fortran one. So finishing a bit a few minutes late, just to let you know that right now there are two channels in Slack. The idea is to kill this one and that we all stay on this one. Some of you were not able to see it, I didn't understand it. Tommaso created this one, and Tommaso will arrive in a few hours. So I think that you can ask him to join it if you are not able to see it. If you don't know who Tommaso is this guy, and you will see him. And when we know who's the group that is interested in these techniques, I will upload, and I will talk to Sunil to upload these extra lectures that we suggest you to watch them before you start actually doing some projects on Fourier techniques, correlations, etc., etc. So I think I will stop there.
Thanks a lot for a very nice talk, Diego. Now time for questions. Yes.
Yes, thank you so much for the wonderful talk. So I just wanted to ask, can you comment on the benefits, the advantages of using a cross-spectral analysis over a cross-correlation function analysis?
I would say it's a difficult question to answer because it would be really dependent on the problem that you have. So it really depends. So for example, it's not the same if you are just studying X-ray light curves at different energy bands, or if you're comparing optical light curves with X-ray light curves. Also the quality of the data, whether there are gaps in the data or not gaps in the data. So there are many things that you have to take into account. So I'll be happy to discuss this if you say, Diego, I have this type of data that I would like to study. What do you think I should be using?
Okay. Yes. Yeah, I'll speak to you on that then later. Thank you about it. And another thing which I wanted to ask, what other information, physical information, can you extract from the CCF profile or the width of the CCF?
So depends. So the CCF basically tells you whether there is. Sorry, let me go a step back. You have two light curves, and that you want to compare, and you see. Let me come back. You have two light curves like these two, E0, E1, where they are similar. So you see that there is a peak here and there is a peak there. But for example, this part is not really here. So that means that while the two light curves are, I don't want to use the word correlated, let me think a second. They are linked to each other, so they know of each other. It's not fully one copy of the other one that is shifted. So depends on how similar they are and how fast they are moving. That is going to change the shape. I keep moving my hand, so I hope you see me. That is going to change, for example, the width of your cross correlation of the main peak, but it will also change the wiggles that you will see later on. And whether it's symmetric or not symmetric, whether it goes negative or positive or stays always positive, will be giving you a lot of information about that comparison between the two light curves. Actually, I would say that, well, nowadays, so for a long time, a lot of people use the cross correlation because it's a simple thing to calculate, and you can do it even if there are gaps in the data, etc. If you have really good data, so imagine if you have nicer data or XMM data, any of the X-ray satellites data will be good enough, and you cut the light curves in two, then you can actually do transform to calculate that phase lag, resolved in frequency. So now you have a much better understanding of what is happening at each part. It's more complicated to model, but you have that information which basically tells you at that frequency you have certain phase lag, and at a different frequency you have a different phase lag. When you do a cross correlation, you have the problem that it's all convolved in one plot, and you don't have the frequency resolution.
Okay, so
I'm not sure I answered your question.
Yes, you did. Thank you. So it's basically about what domain you want to study. If it's energy dependent information that you need, you prefer cross correlation, while if it is frequency information that you want, you might have to use cross spectral studies.
Yeah, and actually, ideally, I would say, and this I would like to hear enough. I would all in the way to have the most amount of the project model, and then good luck. But that would be the way to do it.
Just with unequally spaced data and the definition of the Nyquist limit and the potential for detection of super Nyquist signals.
Yes, so I have dealt times with that. So far that is with that gaps. If you have gaps for data, then the standard techniques that is used is Lom's-Cargill parallelogram. It's very